we have already seen how to get an exact couple from a filtration. So notice that exact couple looks like this. You have this map going from here to here, which is alpha, then you have this map beta, gamma, again you have this map alpha, then you have beta, gamma, again you have this map alpha, beta, gamma, and so on. So notice that now you can have a map like this going from E to E. You call this map as D. So again you can have map going from here to here. You call this map as D. And this D, as you can see from the diagram, you first apply gamma and then you apply beta. So you define the differential of the map from E to E, where D is first apply gamma and then beta. So notice that if you apply this map twice, you will get 0 because you will have this gamma beta in between, and first you apply beta and then you apply gamma, you will get 0 because this couple is exact. Anyway, it comes from the long exact sequence, so you can see here if you first apply beta and then you apply gamma, you will get 0. So again, recall that each of these modules A, E are bigraded. So these maps, when we talk about alpha and beta, they have like a specific meaning on each and every bigrading, as we explained in the lecture on filtration to exact couple. So once you have the differential, we can compute the homology at every point. So since this module E is bigraded, we just focus on particular point PQ. So at PQ you compute the homology, take the kernel of the map going out, obviously from PQ would be going out, the image would be coming from P plus 1 Q, and that is because this map D has bi-degree minus 1 0. Now the bi-degree comes from adding the bi-degree of these two composite maps beta and gamma, and you can see beta just contributes nothing, and therefore the bi-degree is minus 1 0. So basically you add the bi-degree of two maps to get the bi-degree of D. So since this bi-degree is minus 1 0, so obviously it has to come from P plus 1 Q. So Q remains at Q, P plus 1 goes to P. So what do we have now? What have we done till now? So we are talking about page 1. So on page 1 lives the bigraded module E. So I'm writing it as E, but you can picture page 1 as a chessboard where in each square lives a module, and this is a bi-module. So this obviously is of something like this form: P comma Q, E, P comma Q. So on every chessboard lives something like this. From this there is a differential coming out, and this differential has bi-degree minus 1 0. So out of every square comes out an arrow which goes, so minus 1 0 means 1 left and 0 up. So 1 left and 0 up. So that is the differential coming out of every page. So from here you can compute page 2. So compute the homology at every square, put it on the square on page 2. But now we have to compute the differential on page 2. So this is what we have to compute. Since we are going to define this recursively, what we need is another exact couple. So we'll form another exact couple with E2. Obviously this is bigraded just like this was bigraded, and your map, this D in the second graded map in the second page, so this differential in the second page is just the composition. You first apply gamma and then you apply beta, this 2 gamma and 2 beta, and then you can do this process recursively. So before we can apply these two maps, we have to again find out what these two maps gamma and beta are. So first you define this A2. So A2 is just image of alpha. So whatever alpha there is, you replace this by image of alpha. So this is also image of alpha, and this is also image of alpha. Now this this map 2 alpha, this is just same as map alpha restricted to image of alpha. So this 2 alpha is just alpha restricted to the image of alpha. So this is precisely what is our this map. So now you have this map, but now you are just using the map alpha. This is same as map alpha, just restricted to image of alpha. So because you know that alpha goes from A to A itself, so you can keep applying alpha to image of alpha also. So the bi-degree remains the same, 1 minus 1, just the pi degree of alpha, because nothing has been done. You're just replacing this with image of alpha. Nothing has been done. So more importantly, we want to talk about this map 2 beta and 2 gamma. So you take this element y here, and we have to find out in which class does this map to. So notice that elements of E2 are classes because you are modulo out by some image, so they are in some class. So therefore we are going to write it in square bracket. So if you start with y here, you want to apply 2 beta to it. What we will do is this y lies in image of alpha, so therefore it comes from some alpha inverse y here, because alpha inverse y lies in A. So this alpha inverse of y, if you apply beta to it, will lie here, beta alpha inverse of y, and therefore you take the class of this here. So you take the class here. Now the bi degree is minus 1 1. So beta itself is 0 0. It is not going to contribute anything. So all the contribution comes from alpha inverse. So alpha is 1 minus 1. So alpha inverse would be minus 1 1. So you have minus 1 1. So again, this is not complete because we have to show that this map is well defined, it makes sense and everything. That we are skipping, but you can find the details in Hatch's online notes on spectral sequences. Now we have to define this map gamma. So this map gamma obviously acts on a class because elements of E2 are classes. As you can see, you modulo out image. So this element in this class comes from some element z here. So this element z gets mapped to this class. Apply gamma to it, it gets to gamma z here, and this is the same gamma z we use here. So again, this bi degree is minus 1 0 because the only map we are using is a gamma. So again, we have to show that this map is well defined, and if you show this map 2 beta, 2 gamma, and your map 2 alpha as restriction to alpha, you in fact get another exact couple. Now since you get another exact couple, you can repeat this process inductively to get say rth couple like this. So before we stop here, first notice that what is D1 now. So D1 is, again I said, composition of this maps. You first apply gamma and then you apply beta. So what is a degree? So the degree would be, you have to add these two, so you get minus 2 and 1. So your degree is minus 2 and 1. So this is the degree on page 2, and it comes from these two maps, gamma and beta, and you can see these two maps in turn come from the long exact sequence maps. So this minus 2 1 means what? Means 2 left, 1 up. So if you go to the third page, again you will have the bi degree here. It will alpha inverse. Now this alpha inverse will become 2 alpha inverse this. So you have minus 1 1, and then you add up with inverse of this, which will be minus 1 1. So you will get minus 2 2, and then you add up to this minus 1 0. You will get the third differential, which will be minus 3 2. So that is 3 left and 2 up. So you can continue this. So in general, you will have 1 minus r here, r minus 1 here, because obviously you are just taking inverse of this map and adding it up. So on page 2 you had minus 1 1. This was on page 2, as you can see here. On page 3 again, here this will be minus 2 2, because to this you will add inverse of this, which is minus 1 1. On page 4 you will have minus 3 3. So on page r you will have minus 1 minus r and r minus 1. So this is symmetric, as you can see, one is negative of the other, and when you add minus 1 to it, this just becomes minus r and r minus 1, and that's precisely our rule. On page r the arrow is r left and r minus 1 up. So you keep computing homologies, the arrows keep on coming. If you keep on cranking this machine, you get more and more differentials, and you get more and more pages. So from an exact couple we can get a spectral sequence. So you started with exact couple here, you get the second page, from second page you get the third page, from third page you get the fourth page, and so on. And we recover this rule of arrows, r left, r minus 1 up. So in some sense, this exact couple actually doesn't tell you much. It's just a tool to tell you, the pages are coming one after another. But the fundamental idea is that everything comes from the long exact sequence. So in most of the applications, at least the applications that I have seen, everything ends at page 2. So after page 2, almost everything is stabilized. So you have to just, from the long exact sequence, you have to just go one step further. And after page 2, everything starts making sense. It starts getting stabilized. So you don't have to go to the rth page. Page 1 is already given to you by long exact sequence. Only page 2 you have to apply a bit of your mind, like we did it in the snake lemma for from cohomology spectral sequence. And after that, everything will be stabilized. So most likely you get stabilized here only. You don't need to go to 3, 4 and 5. So you get stabilized here only at 2.